So inverse functions. So we're going to first, there's two parts of this. We're going to determine whether a function is one-to-one, and if it is, how do we find its inverse? And then secondly, we're going to simplify expressions of the type f composed with f. This f minus 1 is inverse of f, and inverse of f an f. So what is an inverse? So when we go in for, when we go from an output of a function back to its inputs, we have what we call a reverse relation. So usually what we're talking about relation is we put in inputs and we get outputs. If we reverse the way that goes and we put the outputs back in and the inputs come out, that is an inverse function. So what we find is we basically are just interchanging the first and the second set of coordinates. Or what we're doing is we're taking x and y and they're going to switch places. So we're just going to do this the easy way first. We're going to just take our first and second coordinates of ordered pairs in a relation to produce the inverse relation. So if h was just -8 and 5, 4, -2, -7, 1, 3.8, and 6.2, if I just want to make the inverse relationship, I am just going to swap these ordered pairs. Or like I said, I'm switching my x's and my y's. So the inverse relation would be, now it's 5 goes in, -8 comes out. Now that -2 goes in, 4 comes out. That 1 goes in, -7 comes out. And that 6.2 goes in and the 3.8 comes out. So all we did is we just switched the domain and range, essentially. So the idea of an inverse function is that it's essentially undoes what an inverse relation essentially undoes what the original relation did. So what we want to do is see how this is going to relate to functions. So like I said, inverse relation is just interchanging the first and second coordinates of each ordered pair in a relation produces your inverse relation. So that's just with ordered pairs. So just another example, and we're going to graph this one. So I'm going to graph it like this. This is G. G is going to be green. G is the points 2, 4. And then -1, 3. And then -2, 0. So I am going to do my inverse relation in a different color, this burgundy color. So all we're going to do is we're just going to swap these 2 points. So 4 swaps the 2, 3 switches places with -1, and 0 switches places with -2. This is my inverse relation. So when I graph it, now I'm going to have a point that is at 1, 2, 3, 4, 2, a point at 3, -1, and a point at 0, -2. So one of the things to kind of notice here, so this is a line that is just y equals x. And what we see is that these points are reflecting over this line. So your inverse relation, whatever it's going to be, is going to reflect over the line y equals x. And the reason this is working, because we were saying y equals x basically mean we're switching those points. So what we really want to work on is what we're going to call is dealing with your inverse relations that are equations. So we can't call them inverse functions yet. We have to do some work to make sure it is going to be a function. So if a relation is defined by an equation, interchanging the variable produces an equation of the inverse relation. Meaning, if y equals 3x minus 5, and I want to have my inverse relation, all I do is I'm just going to switch those x and y's. So it's kind of the same idea we did before, is that we had an xy pair, and then we just changed it so it was a yx pair, and that was our inverse relation. So we're just doing that kind of similar thing, it's just with the equation. So my inverse relation just would be x is equal to 3y minus 5 now. And if you wanted to, and you solve that for y, you would have x plus 5 divided by 3. All right. So this one is, I'm not going to be able to solve it for y right away anyway. So we're going to see what our inverse relation would be. So we have y is equal to x squared minus 2x. So my inverse relation just means that I just have to swap my x's with my y's. I have to switch places. So where I have y is now going to be x. And every place I have x now becomes y. Oops. Okay. So I'm going to show you a graph of what this looks like. So what we see here is your blue line. It's a parabola, but that was the original relationship. So we're getting this nice parabola here. What happens is when I do the inverse, if we graph this, we found ordered pairs, which we see right here. So here, if I put in the original relationship, -1, 6 would come out. Well, that would mean that if I put 6 into the inverse, -1 comes out. So that's the point of an inverse, is it's going to switch your domain and range. So what we had here, this point, -1, 6 is this point right here. Well, now that point, if I put in the 6 into the inverse function, there we go, becomes this point right here. So what's going to happen is all these points are going to switch places. So 0, 0, well, that one's actually going to stay in the same place because it's 0, 0. When we switch the domains and range, 0, 0 is in there. The point 2, -6, that's in the blue line. So the original function, the original relation. So 2, -6, about here. And what we see is that to get the inverse relationship, that means that -6 goes in, and now the 2 comes out. And that's pairing with that point right there. And you're noticing that we have that slash line there of y equals x. Once again, mirror image, like it's pushed over there, so it is reflecting The blue line, if we reflected it over y equals x, would give us that red line. So if a relation is given by an equation, then the solution to the inverse can be found from those of the original equation by exchanging the first and second coordinate of each ordered pair, which is what we see right here. X, y now becomes the yx, but we're switching it. So we swap those ordered pairs still. Thus, the graph of the relationship and its inverse are always reflections of each other across the line y equals. So something to notice here is that where the blue line, our original relation, is a function, the inverse relation is not a function. It does not pass the vertical line test. So one of the things we always have to check for to have an inverse function is that the inverse is in fact actually a function. Which brings us to one-to-one functions. A function is one-to-one if an inputs have different outputs, that is, if A and B are not the same, then it's not possible that f of A would equal f of B. Or a function is one-to-one when the outputs are the same and the inputs are, if the inputs are the same, the outputs are the same, that is, if f of A equals f of B, then A and B had to be equal. So essentially what we're saying is that we can't have this happen. If f of A and f of B were equal, then A and B cannot be different and there still be an inverse. Okay. So what you're thinking about is, let's say we go back to that graph again. So if we look at here and here. So what we had was that if we looked at the original line here, we're going to say that this is a f of x. That was the function. That's our f of x. Now, if I put 0 in there, 0 comes out. But we also see over here that f of 5 also produces 0. That means it's not one-to-one because f of 0 equals f of 5, and 0 and 5 are not the same. So what we want to happen is that essentially that I could put in a function value and it's only going to produce that output once. It's not going to duplicate. So this can't happen because as we see, when we do that reflection, then this point reflects over here. This point's going to stay there. It's going to not reflect, but now we have this problem where I'm not passing the vertical line test. So that means that inverse can no longer be a function. So another way to describe a one-to-one function is each input can only be produced from one output. So before we said one input only produces one output, well, now we're adding on the extra that not only one input produces one output, but each output can only be produced from one input. So it's one-to-one. For example, if f was -4, 2, -2, 5, 0, 4, and 2, 9, this is a one-to-one function. Because as you see, none of these y values are repeating. So if I end up trying to do an inverse of this, what you'd end up finding is that the inverse would stay a function still. So as you see here, my inputs only ever duplicate, they only see them once. There's no duplications. They're not producing two different outputs. If you look at the second case, this is not 1-to-1, simply because of these right here. If I put in -1, I'm going to produce 0. If I put in 1, I'm also going to produce 0. It's still a function, but the problem is if I try to do the inverse, and I'll switch these points switch, we'd have 0, -1, and then this would be 2, 0, and then we would have 0, 1, and we have -1, 2. So as you see, when I do the inverse part, the inverse can't be a function because I put 0 in it and it produces 2 different numbers. So this is what we're talking about with being 1-to-1. I can't duplicate x. I shouldn't have the x value duplicate. Sorry, I shouldn't have the y value repeat more than once. It should not come from multiple points. It should only be one point produces it. If that doesn't happen, we can't have a inverse function. We can have an inverse relation, but not a function. Okay. So we need some new notation. If the inverse of a function f is also a function, we can only do this if it's an inverse function, not an inverse relation, we're going to write this f with a superscript of -1. And this reads f inverse. So this is because there's been a mistake in the past. This does not mean we're treating it like it's an exponent. It is a notation to say we have an inverse. So the -1 is not an exponent. It does not mean that we're going to end up doing this. It's not a, basically you're saying it's not a reciprocal. F to this -1 does not mean a reciprocal of f, and f to the -1 cannot be equal to 1 over f of x. Like I said, this only means inverse of f. That is all it means. We can't try to make it into some sort of new function using reciprocals. If a function f is 1-to-1, then its inverse, f inverse is what we're going to call it, is a function. Like I said, just means f inverse is going to be a function. The domain of a 1-to-1 function f is the range of the inverse function. So the domain and range are going to switch places. The range of the 1-to-1 function is now the domain of the inverse function. If a function that is increasing over its domain or it's decreasing over its domain, it is a 1-to-1 function. Meaning, like, if it's increasing, you know, like it looks like this the whole time, it just stays increasing. Or it just stays decreasing. It's going to be 1-to-1 because, as we see, we're not going to have multiple y's pop out from the same x or from different x values. Let's try it again. The same y pop out from different x values. So a function is not increasing or decreasing if it looks like this. So it started decreasing, then increases and decreases again. So when we're talking about being increasing, it means increasing everywhere. Decreasing means decreasing everywhere. This is not an increasing or decreasing function. This one is not 1-to-1. So that's what we mean by increasing and decreasing over its domain. The entire function has to increase or decrease. And then it is 1-to-1. So this is going to bring us to the horizontal line test. If it is possible for a horizontal line to intersect the graph of a function more than once, then the function is not 1-to-1 and its inverse is not a function. So the first case, the function is the graph itself is of a function, but it doesn't pass this horizontal line test. It's meaning like this point here and this point here, they have the same y, but they come from different x's. What happens is that when I try to do the inverse, as we saw before, because everything's going to reflect over this line y equals x. This whole thing reflects and looks like this. And now it does, the inverse doesn't pass the vertical line test and is not a function. So if you want to make sure that your function is one-to-one, it has to pass the horizontal line test. So a horizontal line should only cross the function at most once. So as an example, A is going to pass the horizontal line test. Also notice that the function is decreasing over its whole domain, but it passes the test. So this one would be 1-to-1. B, for one thing, it's increasing and decreasing combined together. It's not just one or the other. It does not pass the horizontal line test. This one is not 1-to-1. So this means that A has a possible has an inverse, B does not have an inverse. And for more examples, we have C and we have D. So if you notice with C, once again, I passed that horizontal line test. This one stays decreasing the whole time. This one will have an inverse. D will not have an inverse. One thing, it really fails here, the cross the vertical line test. There are 3 different x values that give me the same y, which means if I try to do an inverse relation, it's not going to be a function. So these ones you could try to reason out whether it's going to be a function or not, or try to do a quick sketch of what it would look like. These are pretty easy ones. There's only like a small shift to the whole graph. But determine if the following functions are inverses, and then make a sketch if you need to kind of decide which it would be. So I'll give you a moment on that and come back here. So if you did a quick graph of both of these, this is just a parabola shifted down 8 units. So it will look like this. And as we see, I'm not going to be passing any horizontal line tests. This already fails. I have a horizontal line that crosses it more than once. Fails horizontal line test. Not 1-to-1. And we have no inverse function. We have an inverse relation, but not an inverse function. At least not yet. We'll have a way to make those eventually. So B is basically a cubic that's also shifted down and it's kind of squished in as well. It's basic shapes like this. We see this one. I can keep drawing lines, but I'm going to only cross one time. So we're going to pass the horizontal line test. We pass the horizontal line test. That means that it's a 1-to-1 function. And because it's a 1-to-1 function, it's also going to have an inverse function as well.